When a digital infection first breaches a secure network, the ideal defense is an immediate, autonomous neutralizing pulse. The reality is much slower. In financial critical infrastructure, the digital networks powering national banking and sovereign wealth funds, human analysts currently take an average of 47 minutes to respond to a novel advanced persistent threat. An advanced persistent threat, or APT, is a prolonged, highly targeted cyber attack designed to evade detection while stealing data or mapping a network. Traditional SOAR platforms are deployed to close this timing gap. SOAR stands for Security Orchestration, Automation, and Response, software designed to coordinate security tools and execute automated defense playbooks. Yet these platforms fail against 70% of new attack vectors. The structural flaw lies in their logic. Legacy SOAR systems rely on rigid, linear playbooks. They expect clean, predictable inputs. When confronted with unstructured, obfuscated threat data from a novel attack, their pre-written logic trees break down. Human analysts are too slow to react manually, and legacy automation is too brittle to adapt automatically. This leaves a massive vulnerability window open in modern financial networks. The software industry proposes solving this agility problem by deploying LLMs to automate dynamic threat responses. An LLM, or large language model, is an AI system trained on vast amounts of text to generate human-like reasoning and responses. In a critical infrastructure context, this introduces a fatal vulnerability. Standard LLMs operate as probabilistic black boxes. They guess the next most likely token, making them inherently prone to hallucinations, fabricating plausible but entirely false information. If an autonomous AI misinterprets an anomalous network ping and hallucinates a command to shut down a core payment gateway, the defense mechanism executes the exact disruptive outcome the attacker desired. To solve this, the cognitive SOAR, or SOAR framework, introduces a new triad. It synthesizes symbolic AI, vectorized connectionism, and formal verification into a single, cohesive architecture. Deploying an active agent inside a zero-trust financial environment requires engineering a system that operates at machine speed while remaining mathematically and provably safe before any code executes. The foundation of this system begins with a strict deployment constraint: data sovereignty. Financial institutions require a zero-trust, air-gapped architecture, completely eliminating the use of API-based cloud AI models. The Mac Studio M3 Ultra serves as the specialized local hardware enabler. It's a highly compact unit capable of running massive parameter models entirely off-grid. Traditional enterprise hardware clusters multiple GPUs, which creates a memory bottleneck. During heavy inference tasks, data transfers choke on the PCIe bus. PCIe, or Peripheral Component Interconnect Express, is the standard high-speed connection interface used to link internal computer components. This chart details the advantage of Apple's unified memory architecture. The system on a chip natively addresses over 192 gigabytes of high-bandwidth memory without bus latency, easily accommodating the 42 gigabyte footprint of a highly quantized 70 billion parameter model. The remaining memory budget comfortably fits the 128K context window KV cache and the necessary vector database overhead. The KV cache, or key value cache, is the memory mechanism AI models use to store conversation history and process large documents without recalculating data. Subtracting those requirements leaves significant computational headroom for concurrent data ingestion and orchestration pipelines to run simultaneously on the same machine. This unified memory structure provides the physical foundation required to host high-parameter intelligence while maintaining absolute data sovereignty. With the hardware secured, the next layer targets the incident retrieval bottleneck, the process of matching live incoming threats against millions of historical security logs. This visualization compares search efficiencies. Legacy SOAR relies on O of n linear regex matching, forcing the system to scan row by row. At the scale of enterprise data, finding the correct playbook becomes computationally prohibitive. SOAR replaces this with vectorized case-based reasoning. This technique uses transformer models to map complex threat inputs, like obfuscated code, into high-dimensional spatial embeddings, clustering similar threats together based on semantic meaning rather than exact keywords. To navigate this vector space, The system applies HNSW indexing. HNSW, or Hierarchical Navigable Small World, is a search algorithm that constructs a multi-layered probability graph to rapidly find similar items in high-dimensional data. By structuring the data through HNSW graphs, the retrieval complexity drops from linear, O of n, down to logarithmic, O of log n. Mathematically, this reduces a search that previously required 10 million database comparisons down to approximately 24 operations. Breaking the O of n bottleneck yields a multi-billion-fold speedup. This enables the sub-10 millisecond similarity searches required to identify and analyze zero-day exploits in real time. Retrieving a historical incident is useless unless the system can logically reason about how to apply that history to the current threat. The traditional SOAR cognitive architecture is designed to simulate human decision-making through a strict three-step loop: elaboration of the current state, decision on a course of action, and application of that action. Historically, this architecture has been limited by its reliance on a manually curated, rigid working memory. It lacks the flexibility to interpret noisy, real-world data. This flowchart illustrates the Neuro Symbolic fusion process. The high-dimensional outputs from the HNSW vector database are piped directly into the elaboration phase of the SOAR architecture. Inside this loop, the 70 billion parameter LLM operates as a creative synthesizer. It evaluates the retrieved historical cases and generates novel response plans based on fuzzy, semantic analogies to the past. The symbolic SOAR loop acts as a procedural cage. It forces the LLM's generative text to adhere to specific operational goals required by financial compliance standards. Replacing static rules with connectionist vectors inside a symbolic loop grants the AI semantic intuition, allowing it to understand novel threats without sacrificing procedural compliance. The final vulnerability in autonomous execution is mathematical certainty. The system must guarantee that dynamically synthesized response will not execute a self-destructive command. The solution is formal verification using LTL. LTL, or linear temporal logic, is a mathematical system used to specify and verify the behavior of computational systems over time, ensuring rules are never violated. This diagram displays runtime verification in action. The LLM's proposed output is intercepted and mathematically checked against rigid safety parameters before execution is permitted. An LTL invariant acts as an absolute law. For example, a property can dictate, "Always, it is not the case that the critical server is disconnected." The consequence is deterministic. If the LLM generates a containment plan that violates this invariant, the formal logic engine triggers an outright rejection of the command. Commercial LLMs rely on probabilistic prompt engineering, asking the AI nicely not to cause harm. LTL replaces requests with hard mathematical gates. This deterministic fire suppression system elevates the entire architecture from a probabilistic liability into a provably safe, autonomous defender. This 3D blueprint models the completed SOAR framework, locking the 4 distinct layers into a single cohesive engine. The theoretical foundation closes the neuro-symbolic gap, fusing the rigidity of cognitive science with the adaptability of connectionist AI. The mathematical steel provides massive data capacity, dropping search times from linear scans to logarithmic vector retrievals. The automated fire suppression system applies formal methods and LTL guardrails, enforcing a zero-trust execution environment. Defending critical infrastructure requires structurally engineering mathematical trust into every layer of the compute stack. The stakes are measured in macroeconomics. Applied to institutions like the Kai Student Loan Fund, this architecture protects multi-billion-dollar national assets from targeted disruption. By achieving a deterministic, sub-5-minute machine response, SOAR permanently closes the 47-minute human vulnerability window. It satisfies stringent regulatory demands. Every automated decision generated by the agent is mathematically verified and entirely auditable by human oversight. This specific fusion of neuro-symbolic logic establishes a blueprint for protecting other high-stakes environments, from energy grids to military command networks. By solving the triadic gap of speed, adaptability, and safety, cognitive SOAR turns the zero-day threat from an unmanageable catastrophe into a solved mathematical equation.